Hey everyone, and welcome back for another deep dive. Today we're going to be tackling something that's surprisingly relevant to our everyday lives. Calorimetry.
Oh, yeah.
It might sound a little intimidating, but trust me, it's all about understanding how heat and temperature play a role in things like cooking, you know,
Right.
heating our homes, or even how our bodies stay at a comfortable temperature.
Yeah.
I've got some excerpts from the thermodynamics textbook here, and honestly, I'm already finding it way more interesting than I expected.
That's great to hear. What I think is so fascinating about calorimetry is that it really helps us decode the language of energy transfer,
Okay.
which is happening all around us constantly,
Yeah.
you know?
Okay, so before we get too far, I have to admit, I always get a bit confused about the difference between heat temperature and internal energy.
Yeah.
Are they all just different words for the same thing?
That's a really common misconception. They're definitely related, but not interchangeable.
Okay.
Think of it this way. Imagine you're pushing a heavy box across the floor. You're doing work on the box, and that work is a process of transferring energy.
Right.
The box's mechanical energy might increase, but it's not like it's full of work.
Right.
Heat is really similar. It's the process of transferring energy because of a temperature difference, not the energy itself.
Okay, so the heat is the pushing and the internal energy is like the box's energy.
You got it. And actually, the textbook makes a very similar analogy
Oh, wow.
to help clarify this. And this is a key point that the source emphasizes. Heat is a verb. It's something that happens.
Okay.
While internal energy is a noun, it's a state of the system.
That actually makes a lot of sense.
Yeah.
So when we say something is hot, we're not really talking about heat, but about its internal energy.
Exactly. A hot object has high internal energy.
Okay.
It's not full of heat, but it has a lot of energy stored within its molecules. It's like saying you're full of running after a jog. You're not full of running, but you've definitely experienced an energy transfer.
Okay, I'm starting to see the light. And this reminds me of something I read about a scientist named James Joule and his famous paddle wheel experiment. Didn't he do something to demonstrate this whole energy transfer thing?
Yes. Joule's experiment was a game changer. Picture this. He had a container of water with a paddle wheel inside.
Oh,
The paddle wheel was connected to a system of weights that would fall, causing the wheel to spin and churn the water.
okay, I'm picturing it. What happened next?
So as the weights fell, their potential energy was converted into the kinetic energy of the spinning paddle wheel. That kinetic energy then got transferred to the water molecules, increasing their internal energy and causing the water temperature to rise.
So he basically showed that mechanical energy from the falling weights could be transformed into the internal energy of the water.
Precisely. And he was able to quantify this relationship, figuring out exactly how much mechanical energy it takes to raise the temperature of a certain amount of water by a certain amount. This established the conversion factor between joules, the unit of mechanical energy, and calories, the unit of heat. It's like finding the exchange rate between two currencies.
That's incredible. It's like unlocking a secret code between different forms of energy. But wait, does this mean calories are a measure of heat? Like the ones we count when we're thinking about food?
You're on the right track, although we mostly use joules for everything now.
Right.
The calorie as a unit originally came from this idea of heat.
Okay.
It's a fascinating reminder of how our understanding of these concepts has evolved.
Speaking of evolution, what about this specific heat thing the textbook keeps mentioning? I'm getting the feeling it's pretty important.
It is. Specific heat is a measure of how much energy it takes to change the temperature of a substance.
Okay.
Think of it as a material's resistance to temperature change.
Okay.
Some materials are stubborn and need a lot of energy to budge their temperature, while others are more easygoing.
Okay, so is that why a metal spoon left in a hot cup of coffee heats up much faster than the coffee itself?
You're a natural at this. That's a perfect example.
Really?
Metal has a lower specific heat than water, meaning it takes less energy to raise its temperature. So the spoon absorbs heat from the coffee quickly and gets hot fast.
Okay.
The coffee, with its high specific heat, takes its sweet time warming up or cooling down, needing more energy for any noticeable temperature change.
So water is like the thermal tortoise and metal is the hair.
I love that analogy.
Oh.
And this high specific heat of water is actually why places near large bodies of water, like the west coast of the US, often have milder climates.
Oh, okay.
The ocean acts like a giant temperature regulator, absorbing heat during the day without drastic temperature increases and releasing it slowly at night, preventing extreme drops in temperature.
Wow, I'm seeing specific heat everywhere now. It's like a hidden force shaping our world. But there's one more thing from the textbook that really caught my eye. It's this whole concept of latent heat. And it sounds kind of mysterious. What's the deal with that?
Ah, latent heat, the energy hidden within phase transitions. It's the energy involved when a substance changes state, like melting, freezing, boiling, or condensing without any change in temperature.
Wait, hold on. No temperature change. How is that even possible? I thought adding heat always meant things got hotter.
That's where it gets really interesting. It's like there's this secret energy exchange happening behind the scenes. Think about melting ice cubes in a drink.
Okay.
The temperature stays at 0 degrees Celsius while the ice is melting, even though it's constantly absorbing heat from the surrounding liquid.
So where is all that energy going if it's not making the ice hotter?
Instead of increasing the temperature, that energy is being used to break the bonds, holding the water molecules together in their solid form, allowing them to transition into the liquid phase. It's like the energy is busy rearranging the molecular furniture instead of turning up the thermostat.
Okay, that makes sense. So it's like the energy is going into transforming the substance rather than just making it hotter. And that's what they call latent heat.
Exactly. And the same principle applies when you boil water for pasta. The temperature stays at a steady 100 degrees Celsius while the water is bubbling away, even though it's absorbing heat from the stove. That energy is being used to break the bonds between the water molecules, allowing them to escape as steam.
So there's this whole hidden energy exchange happening during phase changes. But why should we care about this latent heat business? Does it really have that much of an impact on our lives?
Oh, absolutely. It's more relevant than you might think. Remember that dramatic example the textbook gave about steam burns?
No.
That's latent heat in action, and it's a pretty powerful demonstration of why it matters.
Okay, you've got my attention. Tell me more.
So think about it. A steam burn at 100 degrees Celsius is far worse than a burn from boiling water at the same temperature. That's because the steam, when it hits your skin, releases all that hidden latent heat as it condenses back into liquid water.
Ouch, that sounds painful. So it's like the steam has this secret stash of energy that the boiling water doesn't.
Exactly. The textbook actually describes how we can calculate like the total energy it takes to turn, say, 1 gram of ice at a freezing -30 degrees Celsius all the way into steam at a scorching 120 degrees.
Oh.
It involved accounting for the energy needed to raise the temperature of the ice melt. It raised the temperature of the water, boil it, and then raise the temperature of the steam. Latent heat plays a big role in that whole process.
So it's like a whole energy journey with these hidden checkpoints where the substance changes form, but the temperature stays the same. That's pretty wild.
It is, and it really highlights how much is going on at the molecular level that we don't always see.
Right.
But here's where things get even more mind-boggling. Did you know that substances can sometimes exist in like unexpected states, like liquid water below its freezing point or above its boiling point?
Wait, really? I thought water always froze at 0 degrees and boiled at 100. What's going on there?
That's where the phenomena of supercooling and superheating come in.
Okay.
These are examples of how substances can sometimes defy our expectations. Supercooling is when a liquid remains liquid even below its freezing point. It's like it's holding its breath, waiting for a trigger to finally change state.
So is that what's happening in those commercial hand warmers?
Yeah.
The ones you click and they suddenly get warm?
You got it. Those hand warmers usually contain a supercooled solution of sodium acetate.
Yeah.
When you click the metal disc, it creates a tiny imperfection that acts as a nucleation site, a starting point for crystallization. And bam, the solution rapidly crystallizes, releasing all that latent heat and warming up your hands.
That's so cool. It's like tricking the substance into changing state on demand. What about superheating? Is that the opposite?
Exactly. Superheating is when a liquid can be heated above its boiling point without actually boiling. It's like it's holding back, waiting for a signal to finally let loose.
Okay.
Have you ever microwaved water and then had it suddenly erupt into a violent boil when you disturbed it?
Oh, yeah. I thought I broke the microwave. It was like the water was possessed or something.
That was likely superheating in action. The water got heated above 100 degrees Celsius in the microwave, but without any nucleation sites like tiny imperfections or impurities for bubbles to form, it remained liquid. Even a slight disturbance like dropping in a tea bag can trigger a sudden, almost explosive boil.
Okay, that is seriously mind-blowing. So are you saying that impurities in water are actually important for it to boil normally, like a little bit of dirt is a good thing?
Exactly. Those tiny bits of impurities act as nucleation sites, providing surfaces for vapor bubbles to form and grow. Without them, the water can become superheated, creating a potentially hazardous situation. It's a reminder that sometimes a little imperfection can be a good thing.
This whole conversation has been one aha moment after another. I'm starting to feel like calorimetry is a lot more than just measuring heat. It's like a key to understanding energy transfer and how it affects everything around us.
I couldn't agree more. It's a really fundamental principle with implications for everything from designing more energy-efficient buildings to developing new technologies for energy storage. And what's amazing is that we've only just scratched the surface of what's possible.
Before we dive into all that list, I need a moment to process everything we've covered so far. This has been an incredibly insightful deep dive into the fascinating world of calorimetry. I'm already eager to see what other discoveries await us as we continue to explore this hidden world of energy transfer.
Me too. And I think our listeners are in for a treat as we uncover even more about how these seemingly simple concepts of heat and temperature are connected to some truly groundbreaking innovations.
Stay tuned, everyone. We'll be right back to wrap up our exploration of calorimetry and leave you with some thought-provoking questions to ponder. Welcome back to the Deep Dive. We've been on quite a journey exploring the world of calorimetry, from the basics of heat and temperature to the mind-boggling phenomena of latent heat and those unexpected states of matter, like supercooling and superheating. I don't know about you, but I've seen the world in a whole new light.
Me too. It's amazing how something we experience every day, like feeling heat or noticing temperature changes, is governed by these intricate molecular processes.
Absolutely. It's like we've been taking a peek behind the curtain of reality, uncovering the secret language of energy transfer. So as we wrap up our deep dive, what are some key takeaways you hope our listeners will walk away with?
Well, first and foremost, I hope we've busted the myth that heat and temperature are the same thing.
Right.
Remembering that heat is a process, a verb, while temperature is a state, a noun, can really help us understand so much more about how energy flows and interacts with matter.
That's a great point. And I think another important takeaway is the significance of specific heat. It's like each substance has its own thermal personality, dictating how much energy it takes to change its temperature. This seemingly simple concept has major implications for everything from cooking times to climate patterns.
Absolutely. And let's not forget about latent heat, the energy hidden within phase transitions.
Right.
It's a powerful reminder that energy can be transferred without any change in temperature, which can have some pretty dramatic effects, as we saw with the example of steam burns.
It's incredible how much we can learn by simply observing the world around us and asking why. It's like we're all amateur scientists constantly trying to decode the mysteries of the universe.
I love that. And calorimetry is a perfect example of how a seemingly basic concept can unlock a deeper understanding of so many different phenomena. It connects our everyday experiences to the fundamental laws of physics.
So as we leave our listeners to ponder all of this, I'd like to pose a final thought-provoking question. Knowing what we now know about calorimetry, what implications might it have on the way we design energy-efficient buildings, cook our food, or even develop new technologies for energy storage?
That's an excellent question. It's a reminder that there's so much more to explore in this fascinating field. Who knows what groundbreaking discoveries await us as we continue to unravel the mysteries of heat and energy transfer.
I can't wait to find out. Thanks for joining us on this deep dive into the captivating world of calorimetry. I hope you've enjoyed this exploration as much as we have.
And remember, there's always more to learn. Keep those curious minds engaged and never stop exploring the wonders of science.
Thanks for listening, everyone. Don't forget to like and subscribe for more insightful deep dives into fascinating topics. Until next time.